Okay, let us start from a short continuation of the previous topic that then will be generalized to the most generic case. So this is called orthogonality of spherical functions. So last time we were looking for the for eigenfunctions of the Laplace operator in 3D, and namely for its angular part that had the following form. Do you remember the formula for its eigenfunction? So the code YLM of theta and phi. Maybe let's use this phi. So there was some eigenvalue. So there are two questions, and the first is what this eigenvalue is, and the second is how to write a general formula for YLM. So what should I write here? Oh, and what should I write for YLM? So there are also eigenfunctions of d and d phi as well. So d and d phi ym of theta and phi equals to im ylm. So do you remember any expression for them? Maybe not the general formula, but for example, what is L0 of theta and phi? Any formula from this family? Mm-hmm. Mm-hmm. And thanks. And the PL of X is what? What is the general formula for it? But this integral could be computed, and we computed it. So, and today we'll need this general formula because it is useful for some computations. Mm-hmm. 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 Thanks. Yes. Correct. And uh, what can we say about this more generic spherical functions? First question: what is the dependence on phi? Mm-hmm. Yes, because the eigenfunctions for D and d phi as well. And what is the do you remember what should be written here? What is the other part? Yes. Mhm. Yes. We have this part. Uh, But it's not all. We also have a sine of theta to power m here. So they are called associated Legendre functions, those expressions. Well, everything is written up to overall normalization, which depends on conventions, but it doesn't matter because we can compute their normalizations and choose it in whatever we like. And do you remember this eigenvalue? Oh, oh. Oh, it's true, but there is also a general formula which looks like this. So, and this is a complete solution of this problem about eigenfunctions of the angular Laplace operator, but we haven't proved it yet, and we'll do this from the general theory. So, but what can we study now is the scalar product between two such spherical functions. Uh, so mm, as you remember, the measure on R3 written in polar coordinates it looks like this: R squared dr d phi sine sine theta d theta. Mm. So we can say that there is a radial part of this measure and there is a angular part, which we call ds, dA. Mm. And this ds is d phi sine theta d theta, which is same as to say it's d phi d cosine theta. It's useful because we have cosine is the main argument of any function. And now let us take this measure and try to compute a scalar product between different spherical functions. So in principle, we already know that they should be orthogonal because Laplace operator was self-adjoint, so its eigenfunctions should be orthogonal. But let us try to see this computationally. So first, what can we say about the following integral? Uh, Integral over ds over the whole sphere y l m of theta phi y conjugated. Let's try m prime of theta and phi. Yeah. So what can we say if m prime is different from m? And y. Yes.
Because when we integrate with respect to phi, the exponentials cancel out.
Yes, thanks. Yeah, this is because integral in phi e to I m minus m prime phi, well, m prime minus m phi equals to 0 if m is different from m prime. Yes, so the 0 for this reason. But now let us study the situation when m equals to m prime. But L is different from L prime. And let's first study the case m equals to 0. So we need to compute the integral in dx. So we can write this measure as d phi dx. So phi integral equals to some number, it does not matter, like 2 pi. And we need to compute the integral in dx and in what limits, by the way. So it's cosine theta, it spherical coordinates look like this, and theta is measured from the z axis, so it changes from -1 to 1. So, and actually, we can do even. Let us compute this integral, but usually we can compute even more general expression. Let us also assume that L is less than L prime. So we have this integral from -1 to 1 dx, some number del and dxl. So the idea is the following: we can integrate this integral by parts. So mm, all the boundary terms will cancel because if we differentiate x squared minus 1 to power l prime less than l prime times, then we'll get something proportional to x squared minus 1, so it will vanish at the boundaries. So this integral will equal to some number times integral from minus 1 to 1. So, what can we say about this if we know that L prime is greater than L? What can we say about this expression? What is its degree in L? Mm-hmm. Mm-hmm. Thanks. Yes. So if we differentiate it L times, which happens when we need to compute the norm of PL, it will be some number. If we differentiate it one more time, this number will vanish. So we will differentiate constant. So it equals to 0. And so the integral itself is also 0. And we can notice that the only thing which was important was that this polynomial was of degree L less than the degree of this polynomial. So in the same way, we can show that integral from minus 1 to 1 dx x to L, L prime of x is 0 when L prime is greater than L. So the statement is the following: this Legendre polynomials could be obtained as a Gram-Schmidt orthogonalization of a monomial basis on the interval from minus 1 to 1. So so they come from Gram-Schmidt orthogonalization. Mm. We first take basis that consists of 1, x, x squared, uh, x cubed, and so on, and then correct each next monomial by a linear combination of previous monomials such that it becomes orthogonal to all previous monomials. So and that we write that P0 equals to 1, P1 equals to x, P2 equals to, well, they are defined with some coefficients, but let us say that we have some other normalized polynomials. It will be x squared plus some coefficient times 1. And we need to find this coefficient from a requirement that P2 tilde scalar product with P0 is 0, and so on. So this formula written here describes the results of this procedure of orthogonalization of a polynomial basis on the interval from -1 to 1. And we have checked this here, that it is indeed the answer. So to me it looks like some natural question. And the answer is a bit non-trivial, and comes actually from a different problem, from 3 dimensions, from Laplace operator, and so on. Are there any questions about this? So we managed to solve this problem for m equals to 0. Now let's go to the general n case. So we need to compute this scalar product. Into the integral from -1 to 1 dx 1 minus x squared to m, because it comes from both Legendre functions of some number. Like this. And now we can use the same argument. And to do this, let us first answer the following question. What is the degree of this term here? So it's polynomial, because 2m over 2's combine into 1 minus x squared to the power m. What is the degree of this polynomial? Yes. Thanks. So, here we have L prime prime plus m's derivative of another expression. So if we do this integration by parts again, we will get 0 using absolutely the same argument. So this is less than uh, L prime plus M. And we move this derivative integration by parts to this first factor and get zero. We should only care about these boundary terms because uh, uh, this expression differentiated more times does not vanish the boundary, but this expression vanishes. We should look at this a bit more carefully, but it will work. So, so we see this orthogonality property. And this should remind us also orthogonality of this simple functions like of exponential or sines or cosines. So, mm, so it will be the general phenomenon. Are there any questions about this? So, if not, let's move to the general situation. So, and the general situation is described by what is called the Sturm-Liouville theory. Uh, this theory that describes solutions of the following equation. Maybe let me first let me write this equation explicitly without introducing a new operator for now. Mm. So uh, in other words, mm, it is a problem about eigenvalues and eigenfunctions of a so-called Sturm-Liouville operator. So, so the problem is to find the maybe we can add here some label. So this operator is what we get if we divide everything by w of x. So and if you look at the um, angular part of the Laplace operator, you see that if you are restricted to given M sector, then it requires precisely this form. So let us write this Laplace operator for given M sector. So we're writing it maybe minus Laplace operator. This will be in this coordinates d in dx, dx 1 minus x squared, d in dx, maybe let us act on some function. Then this operator acts on a function, and then we multiply it, and then differentiate again. So with minus sign. So can you write P, Q, and W in this case? So is it clear that we will get this expression starting from that expression?
W equals to 1 and P equals to 1 minus x squared,
Mm-hmm.
and Q equals to x squared divided by 1.
Mm-hmm. Yes. And if we want to pass from that here, then the change of coordinates is as usual x equals to cosine theta. Hmm. But in this case, this problem, I would say, is for generic second-order differential operator, because it depends on three functions, p, q, and w, and you can write any operator in such form, even without changing the x coordinate. We have uh, we had three coefficients originally, and we have three functions parameterizing this operator. So it's a generic problem. The only restriction is that to have a well-behaving problem, we need to impose some restrictions on these functions. So, and let me list those restrictions. Uh, so first, x lives on a finite interval. So in principle, it's not necessary. We can study these problems also on the infinite or on the semi-infinite line. But for for our problems, it's sufficient to study this interval. Mm. So, so in our case, this interval is from -1 to 1. So second restriction is that W of x is greater than 0 mm, on this interval. Maybe or maybe it's not in, on the open interval. Sufficient to do like this. Then condition that holds always is the following, that p of x should be greater than 0 on the open interval. But then we have different options. And also one last condition is that q of x should be greater than some. So q of x should be restricted from below, but without loss of generality, we can achieve this operator by a constant and say that q of x is constant. So there are these positivity conditions, and now we need to say something about boundary conditions for this problem. Because, for example, if you remember, problems were solving on the interval with all these functions constants, we required vanishing of either of psi or of its derivative at the boundary. So we should do the same here, but these conditions depend on whether p of x vanishes at the boundary point or not. So so there is option 1. If p of a is 0, then the only boundary condition is that psi of a should be regular. Or we can say that psi of a is other than infinity. It's equivalent. And the same for b. So we have already seen this in this case of Legendre polynomials because they did not have to vanish at the boundaries. They were simply polynomials. And later we will see why in this case, this is a real restriction. Why a second solution of this equation behaves in a different way. So, but so this was this case for Legendre polynomials when it is at 1 and minus 1. But there is also a case that corresponds to simply a second derivative, and P of A is different from 0. So, if P of A is greater than 0. So in this case, we can consider arbitrary boundary condition. Alpha 1 psi of A plus alpha 2 psi prime of A equals to 0. With an extra condition like alpha 1, alpha 2, probably greater than 0. Greater or equal than 0. Which is needed for some positivity, and we'll see this later. And the same for another boundary. Well, are there any questions about this? Yeah. Yes. So far we have already seen several examples of solutions of such equations, but so we can assume that they at least exist, and assuming that they exist, in a sense, we have a second order differential equation, and we can solve it. So some solution exist, and but we need to study their properties related to all these boundary conditions, and we will do this now. So let me take one. So the main property which follows from this form of the operator is that if we have two different um, psi's with different eigenvalues, then they are orthogonal. So maybe first property. If L psi one maybe even before that, well, we'll prove it as a zeros property. Uh, and this psi1 is orthogonal to psi2. With the scalar product defined in the following way. So integral from a to b dx w of x bar of x g of x. So let us let me maybe first formulate zeros property. That L is self-adjoint with such a scalar product. Which means that scalar product LF with G equals to F with LG. Let's prove this property. So let's compute this scalar product. So integral from a to b. So do you have any questions about this expression? I simply used the definition of a scalar product with weight function w of x and the definition of the Sturm-Liouville operator and written on this integral noticing that the weight function cancels.
Why do we put the conjugate operator only on f and not on the entire expression?
But what? Because they are real, all of them.
Okay.
Yeah. Mm, Probably we can try to develop something like this with complex functions. No, probably it. Uh, if you want this operator to be self-adjoint, then this functions. I know in principle we have options to write something complex, but I don't want to do this. So they all are real, and in our case, even positive. Yes. So we have this expression, and we see that this part is already a kind of symmetric in F and G up to this complex conjugation. So if you consider this expression, this part will be absolutely the same. Uh, and to say something about this part, we need to integrate it by parts once. We need to move this derivative to this term. So, but we will have the boundary term, which appears during this integration by parts. So this boundary term is what? It is uh, p of a d f bar f bar prime of a f of g of a. Minus the same expression at the upper boundary. So we have this. Uh, plus integral from a to b. Okay, so um, we have such an expression, uh, and we need to compare it with another expression. And so, who can tell me what we should get in this case. So maybe the first question is about this part of expression. What should it be?
We just exchange the rows of F and G,
Mm-hmm.
but keep the conjugate on F.
Mm-hmm. Yes. Yes. So, but this expression is symmetric and exchange F and G. So, and this as well. So this integral is the same. Mm. Yeah. And um, about this part, yes, we should move this prime to G, to be P of A, F of A bar, and G prime of A minus P of B, uh, F of B bar G prime of B. So if we start comparing them, then yes, this is literally the same. And we need to pay attention to the boundary conditions. Yes. So if no, this is P of A. So the first observation, if P of A is 0, if we are in this situation, actually we probably maybe remove all pathological cases, we should also require that psi of x uh, is finite as well. I don't remember, maybe it's enough to ask for psi, but maybe both of them. Yes, so if P of A is 0 or P of B is 0, then both of these terms cancel simultaneously. If one of a function or derivative vanishes at the boundary, then it's also sufficient to say that this terms vanish simultaneously, and we don't need to care about them anymore. The only tricky situation that should be studied is this mixed boundary condition. Mm. And let us study this. With alpha is different from 0. So we know that f prime of A is minus alpha 1 over alpha 2 f of A. And the same for G, because the boundary conditions are the same for all functions. So let us study this difference. Let's substitute this derivative in terms of function itself. Mm. So and this equals to 0. So this is a bit unstable computation for mixed boundary conditions, but we have already proved that this equality holds. So it's indeed self-adjoint. But to be honest, to say that it is self-adjoint, we need to think about a domain on which it acts and on which conjugate operator acts. But let's omit these details. Mm. So, are there any questions about this computation? So. This was a comparison between this term and this term. So mm, let us now use this fact to prove the first statement. By the way, there is a corollary of this that eigenvalues of L are real and well, in our case, positive. So, so this is super easy to prove because we know that uh, L psi scalar product with psi equals to psi scalar product with L psi. So if psi is the eigenfunction, then this turns into lambda psi scalar product with psi equals to psi scalar product with lambda psi. So it equals to so this equals to lambda bar psi psi, and this equals to lambda psi psi. So lambda equals to lambda bar. So they are real, and now let's go to proof of the first statement. Now, let us consider the analogous scalar product, but with L psi 1 and psi 2. So we know that there is this equality, right? psi1 and psi2 are two eigenfunctions. And since the eigenfunctions, we can write that it is equal to lambda 1, psi1, and psi2 scalar product. And this, so what is this scalar product equal to?
Lambda 2,
Yes. Yeah, thanks. So these two expressions equal. Therefore, lambda 1 minus lambda 2 times psi1 psi2 equals to 0. But since lambda 1 is different from lambda 2, then psi1 psi2 equals to 0. So the end of proof.
So it was a more general thing because we never used the expression of L.
Yes, of course. This is because this follows from self-adjointness of this operator. And and to do this, we had to know the scalar product, and this scalar product is encoded in the form of this operator. So it is in the coefficient front with this derivative. So, and this is more the reason why this general theory exists and works. So now, are there any questions about this? So, well, these operators can be thought as more or less Hermitian or symmetric matrices, but of infinite size. So we know that if lambdas are different, then the solutions are orthogonal. But there is a natural question. This operator was of second order. So in principle, we could try to take another solution of this equation that corresponds to the same eigenvalue lambda and ask, can it be another eigenfunction for this Sturm Liouville operator? And it's maybe it can maybe code another property of this operator, or maybe we can just study what happens to what can I erase actually. Probably I can erase everything except the definition of this operator. Maybe let's call it another property. Wait a second. So, in order to prove this, we need to introduce the object called Vronsky. Wronskian of f in G is equal by default, by definition, to f prime of, so it depends on x. And it equals to f prime of x, g of x minus f of x, g prime of x. So now why we need this Wronskian? I would like to prove the following statement. So if we take two solutions of this second order equation with the same eigenvalue, then the following expression, Wronskian times p of x will be constant. So let us prove the statement. So to do this, let us write both these equations in a slightly better form. So we can multiply everything by w and say that p of x f prime of x prime equals to k of x f of x minus lambda w of x f of x. Right. So I've simply written this equation for this operator. And now let us multiply the first equation by g of x and second equation by f of x and subtract. what will we get in the answer? Will we have anything on the right hand side?
Q of x, that cancels.
Yes, because it is a. Mhm.
And on the left side,
Well, it will be just g of x, g of x, prime of x prime, by definition, minus the opposite. F of x, g of x, prime of x prime equals to 0. So um, I will probably erase these conditions and simply remember some of them if I need to compute something. Yeah, so we have obtained this equation, and now let's compute these derivatives. So what happens if we compute derivative of p? We get precisely our Wronskian, because multiplied by p prime. So actually I forgot to indicate the x dependence here explicitly. So we'll have p prime of x times f prime of x, g of x, minus g prime of x, f of x, this term. And there is another term when we differentiate f prime. Yes. Yeah. And what happens if we differentiate Wronskian of f and g? How many terms will we have, and how many terms will cancel? So the,
F sec of the xg minus f g sec of
and this is because when we differentiate the second function in each product, they become f prime g prime, f prime g prime, and this cancels. It's in some sense the same computation as we need to do to prove self-adjointness of this operator. So everything follows from each other. So we see that this expression is Wronskian, and this expression is Wronskian prime. And this is Wronskian, this is Wronskian prime. So combining all this together, we get this statement that p prime Wronskian plus p Wronskian prime equals to 0. So p of x Wronskian of f g of x prime equals to 0. So uh, uh, so we know that the Wronskian of f and g of x equals to some constant over p of x. And now let us consider different situations. So, situation 1. If P of A vanishes at the boundary, what can we say about this constant? Is it a normal situation for our problem or not? Well, I've already raised these boundary conditions, but the boundary condition for such a situation was that the eigenfunction should be regular at the end of interval.
So see,
Yes, thanks. And if it's 0, it means that this Wronskian is 0. But what can we say about these functions if their Wronskian is 0? Wronskian of f and g equals to 0. So f prime g minus f g prime is 0. So uh, f prime over f equals to g prime over g. So it's derivative of logarithm. It's also derivative of logarithm, and they differ by constant. So the only solution of this equation is f equals to some constant times g. So f and g are proportional. They are not actually independent solutions of this equation. So it's the end of proof in this case. Now let's go to the second case when p of a is different from 0. So p of a is different from 0, and we know that in this case these functions should satisfy some mixed boundary conditions. So it's the most general setting. So we know that f of a plus alpha 1 plus alpha 2 f prime of a is 0, and we know that alpha 1 f g of a plus alpha 2 g prime of a equals to 0. So those are these two boundary conditions. Let us suppose for generality, for general, well, suppose that this alphas are different from 0, because if one of them is 0, then either f or f prime is 0, and this Wronskian should vanish at the boundary. So suppose that they are different from 0, and multiply the first equation by, well, actually we can do both. Let's multiply this by g of a, and this by f of a and subtract. So what will we get here? So this first terms cancel because f times g is minus f times g is 0. Yes. Oh, to be precise, that it is alpha 2 Wronskian of f and g of a is 0. And in principle, we could multiply them by g prime, uh, and f prime, and in this case, this would be minus alpha 1 Wronskian of f g of a is 0. So for either, so if at least one of these coefficients is non-zero, as it should be, then we conclude that Wronskian should always be 0. So it is 0 at one point, and since it is given by this formula, we conclude that that in this case c is also 0, and we are again in the same situation. Right? So it was the second property, and it's not the last time when we are using a Wronskian. So now while this computation is still on the blackboard, let us prove one more statement about the Sturm-Liouville operator. So let me think. Probably this would be enough. And we can erase this. So a property of for any f. Uh, so this operator will be positively defined. And to do this, we simply take the previous computation and substitute f equals to g. So So we have already integrated this by parts. We can simply specialize this formula. will be integral from a to b dx p of x absolute value of f prime of x squared plus q of x absolute value of f of x squared. So these are positive or at least non-negative. Well, this is positive. And we need to look at the boundary term again. Yeah, so this is positive. And for this term, we substitute f from this boundary condition, f prime. So it will be equal to p of a minus p of a alpha 1 over alpha 2 absolute value of f of a squared. Yeah, there were conditions like alpha 1 times alpha 2 should be negative and beta 1 times beta 2 should be positive if I do not miss those signs. So this expression should also be non-negative. Well, this Yeah, and so this operator is negative, and we can actually say that it is bounded from below in a sense that this if Q has a minimum, then we can even say that this term is greater than mm, uh, minimum of Q of x for x in AB times f times f. So this expression is bounded by this term. But it's not very essential. Okay, are there any questions about these properties? So, and maybe while we still have Vronsky on the blackboard and we have this computation, let us prove one more property. This is a property which is quite important for the study of high eigenvalues and about studying the asymptotics of eigenvalues. It's a property that describes distributions of zeros of solutions. And maybe it's better not to formulate it in words, but to draw some pictures and say that these pictures always look the same. Mm. So we are in the following situation. We have psi1 and psi2 that correspond to lambda 1. So lambda 2 and lambda 1, and lambda 2 is greater than lambda 1. Or there is even more general setting. When we consider two operators with the same P and Q and with different W. So we have P1 equals to P2, and Q1 equals to Q2, and lambda 2 times W2 is greater or equal than lambda 1 times W1, or maybe let us say simply greater than lambda 1 W1. Mm. So we are in this setting. Then, if it is true, then zeros of psi1 and psi2 are located as follows. So so these are zeros of psi2, yeah, of psi1. And those are zeros of psi2. So if we formulate it in words, we can say that each interval between zeros of psi1 contains at least one zero of psi2. And if you look at the simplest example with trigonometric functions, it is clear that if you take a function with more oscillations, then its zeros will be located between zeros of a function that has fewer oscillations. And it is also true for Legendre polynomials, but in that case it is not that obvious. So Let us now try to prove this statement using Wronskian. So is the formulation clear? So, so Wronskian is defined there. Okay. By the way, I can cheat here a little bit. No, probably I will not do that. I will write this computation again so that you can compare them. So now we're in this statement when we have two functions, psi1 and psi2. So we have p of x, f prime of x, sorry, psi1 prime of x prime equals to q of x psi 1 of x minus lambda 1 w1 psi 1 of x. And the same for psi 2. So now we do the same. We multiply it by psi 2 and this by psi 1. And subtract. So what do we get in the left-hand side? We did all these computations with Wronskian before, so do you know what this expression will equal to? Also, so it will be w of it will be p of x w of psi1 psi2 of x prime, right? This is what we already computed. But what we will have in the right hand side?
psi1 times psi2
Mm-hmm.
times
Oh, this is difference, right? Right. Yeah. So let's uh, so for now we only need to know that this expression is positive because lambda 2 w2 was greater than lambda 1 w1. So, and this computation can be checked explicitly, and we already did this when the right-hand side was 0. So here we only need to know that this is positive. And this P of x is also positive. So let's also write this Wronskian in the corner. W of psi1, psi2 is psi1 prime of x psi2 minus psi2 prime of x minus psi1 psi2 prime of x. So we know this equality, and now let us try to check if it is consistent with an assumption that there are two such zeros of psi1, that there are no zeros of psi2 between them. So suppose uh, so yeah. Oh, so now zeros of psi2 between two zeros of psi1. Let's call them x1 and c and d. So this picture looks like this. We are free to choose all the signs of these functions. So there is point C and point D. So a function psi1 goes like this. It is psi1. And there is also psi2 that does not change sign since it does not have zeros in this interval. So there is some psi2. Now let's look at the value of Wronskian at the point C. So can you say whether it is positive or negative if you look at this definition? So mhm. Yes, yes. So it is a psi1 prime of C times psi2 of C, and the second term vanishes because it is 0. So it is greater than 0. And what about W of D? Mm-hmm. Yes, well, because derivative of psi1 is negative, and psi2 is still positive. So it is psi1 prime of D times psi2 of D is negative. So this Wronskian changes sign. It's on the one side. On the other side, we know that we can integrate this expression and get that P of C W of C mm, minus P of D W of D. No, sorry, vice versa. P of D W of D minus P of C W of C is the integral from C to D Тоді е, psi1, psi2 dx. I simply integrated this expression. So this integral is positive because psi1, psi2, and this term are positive. So, and this is negative because both terms are negative. So it's a contradiction. Yeah. Yeah. So maybe, I don't know, maybe there was too many different statements for the same lecture, but if you wish, you can read the bronze lecture notes. It is even close, maybe up to some notational definitions. Yeah, so, yeah. And do you have any questions? Yeah. Well then, thanks for your attention. See you tomorrow.